Okay, so we've got two examples today. Both involve penguins, so I'm in a good mood. And we can really. So there's an argument for energy actually being the first thing that you should study about physics or science, because it's so easy. You're just adding, subtracting this total stuff. The penguin has this stuff, kinetic energy, because he's moving. There's going to be some friction on him. It takes the stuff away. Okay, even little kids can understand. I get stuff. Stuff gets taken away, candies, toys, etc. But I don't know. I disagree with that because at this level we need to know what the stuff is, and if you've never heard of force or displacement or anything like that, then you don't really know. But don't be surprised. So don't make it harder than it needs to be, and don't be surprised if it feels really easy. It kind of is. Okay, so we have a 10 kilo penguin and he slides on level ice. The coefficient of kinetic friction, because he's sliding, is just zero point 0.1. It's pretty slick. His initial velocity is 2 meters per second. How far will he slide? Well, we could go through all the trouble, like in chapter 4, calculating his acceleration, all that kind of stuff. Okay? But we could also just do energy, especially if, uh, if we've got the formulas memorized. His starting kinetic energy is 1 half mv squared, which is 1 half times 10 times 2 squared is 20 joules, right? Yep. Okay. The force of friction, now I knew it was gonna come to this anyway. The force of friction on a level surface, have you got it stuck in by now? Stuck in your mind? Oh, I see some nods. Okay. It's the coefficient of friction times the normal force. And on a flat surface, start just skipping to mu times mg. Okay, he weighs 10, mu is 10. Oh wait, that's just 10. 10 newtons of friction force. Okay. Now the only hard part of the problem is that friction force points backwards. Okay, so the angle between where he actually goes, the displacement, and the friction force is 180 degrees. Okay, you don't really have to talk about angles and stuff if you get the feel for it. The force is in the opposite direction, so it's going to subtract his energy. Okay, so you have 20 joules minus your 10 newtons of friction times delta x equals 0. Okay, that's the whole problem. If he's taken away, you can even think of, excuse me, joules is newtons times meters. Okay, so newtons is joules per meter. How many joules, if he's losing 10 joules per meter, how many meters can he go before he loses 20 joules? Oh man, that's an Algebra 1 problem. Okay, if I want to do the whole deal, does it ask for the work done by friction? Yeah, it says work done by friction is the change in kinetic energy. So yeah, if I was a professional physicist, I would have to say WF equals delta KE equals minus 20 joules. Okay, but that's going to be the same thing up there. I'm going to lose 20 joules as I come to a stop, right? And I don't have to. How do I know he has no kinetic energy at the end of this problem? Will his mass decrease to 0? No, the problem's over when the velocity does. Okay. So different kinds of energy, actually. I could still have some energy left, just not kinetic energy. How far will he slide? He comes to a stop. Awesome. Okay, let's see. Is there anything else I want to say with that? Aha. Until you get used to it, the work done by the force would be the force of friction times the magnitude of force of friction times magnitude of displacement times cosine of the angle between them. Okay, we wrote that down last time. If not, write the angle between So you are totally free to do 20 times delta x times negative 1, and that's our negative 20. Okay, cosine of 180. If you're not sure what formula to use, you definitely can use that one. Okay, the work is always the magnitude of force times magnitude of displacement times the angle between them. Sometimes it's 0, sometimes the angle is 0, so the cosine is 1. Sometimes it's 180, like here, so the cosine is negative 1. Sometimes there is a weird angle, like we saw in example 1. Good, and the work is always equal to the change in kinetic energy. That's how we got energy in the first place. We messed around with equation 3, yes? Zero. I will have zero kinetic energy. That's what... Oh, I didn't write the whole thing. Good question. Okay. Let's see if we can still zoom in, but slide down. In fact, I think that's what we're going to say at the start of the next one. Okay. Awesome. If you want to, so I don't advise this, maybe one time in the examples, once or twice. You say energy is conserved. You're an astute physicist. Energy can never be created or destroyed. Because if it did, we fooled ourselves. We just built energy out of all the stuff that's already there anyway. If we think it's destroyed, we lost track of it. If we think there's more, there's something in our problem we didn't keep track of. Like, it's our fault if the energy changes. We made a mistake. It can't be. It can't be changed. Okay? Because it's just built out of this stuff that doesn't change. Um, the energy is literally our ability to keep track of all the physics stuff. So, you would have your starting total energy, or well, let's say start and finish. Oh, and we're going to have the work done by friction. Okay. Oh no. No, that's not what I want. It's not. It actually is not going to be equal this time because we got friction draining some away. What we can say though is the work done on the object is the change in kinetic energy. And that's because, remember how we wrote force, which was mass times acceleration, times delta x is 1/2 mv squared minus m 1/2 mv0 squared. That was how we got energy in the first place. Can you see equation 3 like buried in there? Okay. So it has to be the change in kinetic energy. If I started moving and then I stopped, oh no, and it's final minus initial. That's right. It stops at the end, so it's 0. So that's where I got my minus 20 joules. Okay, so some force. In fact, if all I know is the penguin slides forward and he loses 20 joules of kinetic energy because he comes to a stop, some force must be pointed away from him, and the product of that force times his displacement is equal to minus 20 joules. We got to it eventually. Does that work? Does it work literally? Yeah. Why is it, sorry? Oh, okay. How did I magically come up with 20? Was my force of friction 20 newtons? No, it wasn't. Good job. Okay, we'll fix that one. The force of friction was actually just 10, so it should be he slides 2 meters forward. Okay, is our final answer. I forgot to answer the question. Okay, good. Yep, sorry. It's a struggle. We'll pause there. I can cut the video.